So, talking about chemical reactions and the language that we use and the translation between words and symbols, and I'm just going to do a few of these and talk about some stuff, and then we'll think a little bit about writing correct formulas. We'll think about balancing. Again, the whole thing is more or less background for you, in as much as you can type in formulas to your search engines and get the correct words, or type in words and get the correct formulas within reason, although there are still some rough edges around that. But again, it'd be interesting, good for you to sort of see at least how this whole thing works. So here we are, we're presented with a sentence telling us about a chemical change. Solid copper reacts with aqueous silver nitrate to produce solid silver and aqueous copper 2 nitrate. Copper 2 being the stock number that refers to the ion here. Nitrate, of course, is a polyatomic ion. We're given phase information here, and all we got to do is translate it into that. So you would then say solid copper. Solid copper is simply Cu with a little subscript for an S, right? It doesn't have any charge because right now it's full valence shell and everything. Going to react with aqueous silver nitrate. Silver, symbol Ag, nitrate NO3. Silver is one of those transition metals that always takes on a characteristic charge. That charge is +1, and hence +1 -1. Ag NO3 is silver nitrate, and we put a little Aq there to indicate that it's an aqueous solution. Produces solid silver and aqueous copper 2 nitrate. Solid silver would just be Ag, S, and aqueous copper 2 nitrate, here Cu. But because copper is a charge of +2 and nitrate is a charge of -1, we would have to write in O3 taken twice, and again Aq, aqueous, for the phase there. Everything's written correctly, and all we got to do now is inspect to see whether or not the law of conservation of mass is respected. Here's one copper over here, there's one copper over there. There's one silver here, there's one silver there. There's one nitrate here. Remember I told you that those polyatomic ions mostly stay together when they go through a chemical reaction? There is, two nitrates over there. We had to have the 2 nitrates. We had to have them because the thing that forms is copper 2 nitrate. We don't have any wiggle room there. We do have wiggle room is in adjusting the amounts, and I hope you can see that 2 nitrates requires that we have a 2 here in front of the whole formula, and now we have 2 nitrates and 2 silvers. We only have 1 silver here, but that's easy enough to fix. We just put a 2 there, and now you end up with the balanced chemical equation describing this chemical change. Pretty straightforward. Again, a couple more just to sort of illustrate this thing. Write chemical equations for each of the following. First, get the formulas correct, then worry about balancing. This is super important. The formulas have to be correct. The balancing is really kind of a trivial thing unless we're focusing in on predicting the absolute amount of products, and then we have to have a balanced chemical equation. But in this case, hydrogen peroxide in an aqueous solution decomposes spontaneously to yield oxygen gas and liquid water. Hydrogen peroxide is has the peroxide ion in it, O2, 2 minus, and hence the correct formula for hydrogen peroxide would have to contain 2 hydrogens in order to balance the 2 minus charge of the peroxide ion. It's in aqueous solution, so we put AQ there. Spontaneously decomposes simply means we have an arrow, that it all by itself decomposes into something else. And remember that I actually mentioned to you that that peroxide ion, because oxygen is in the -1 oxidation condition, is relatively reactive and unstable. And here's an example of that. Just sitting by itself, it spontaneously decomposes into oxygen gas, O2. Remember, oxygen is always diatomic for the reason that it bonds with itself, and liquid water, H2O, L, liquid, right? And there we go with the correct equation. Now we ask ourselves, is everything balanced? Here we've got 2 hydrogens here, 2 hydrogens there. We got 2 oxygens here, we got 3 oxygens there, yikes, we're in trouble, we're gonna have to fix it. Well, the way we fix it here, of course, is to go ahead and double up here to now have 4 hydrogens and 4 oxygens. And then all we have to do is put a 2 there, and we have the correct number. 4 oxygens, here's 2 oxygens, there's 2 oxygens, and we're good to go. And once again, all that means is that 2 moles of this produce 1 mole of that and 2 moles of that. So again, just a way of accommodating the requirement that the correct formulas be written. One more, and then we'll move down and do it the other way. Solid sodium oxide reacts with liquid water to produce aqueous sodium hydroxide. Well, solid sodium oxide, going to have a formula Na2O. Remember that oxide, the simple ion of oxygen, has a 2 minus charge. Sodium has a 1 minus charge, and so we need 2 sodiums to balance that. That's according to our rules for ionic compounds. Again, that's a solid. Reacts with liquid water. Water is so ubiquitous in chemistry that it is essentially given its common name in all normal circumstances, although it would be formally called dihydrogen oxide. We just use liquid water. Water is in widespread use, and so it's okay. Reacts to produce aqueous sodium hydroxide. Sodium hydroxide, NaOH hydroxide, a 1 minus polyatomic ion, sodium a 1 plus polyatomic ion, aqueous solution there. And there's our balance, our chemical equation, where everything is written in the correct form. Once again, we never worry about the amounts until we've got everything written in the correct form. 2 sodiums here, 1 sodium there, yikes. 2 waters here, 1 water there. Easy to do, we just double up right here, and we end up with a balanced chemical equation. 2 sodiums, 2 oxygens, and 2 hydrogens. All is right with the world, and again, no big problem. And most of these equations will lie down pretty easily in terms of just putting in a couple of coefficients to balance out the amounts. How do you go the other way? Well, similar process. Again, you don't necessarily have to worry too much about this because you can just type in to Wolfram or Wikipedia and get the names of this stuff. But here, just go ahead and read it right off there. Just stare at the compound and you know, haha, metal, non-metal, got to be ionic. Lead, transition metal, got to declare its charge. There are 2 chlorides with it. Chloride has a -1 charge, and so this must be the lead that has a +2 charge. So we just call it that, lead 2, right? And away we go. Here, same thing. CrO4 is a polyatomic ion, chromate. It has a 2 minus charge, and sodium then has to have a +1. It always has a +1 charge. That's why we need 2 of them to balance. Here now, lead, chromate, and sodium chloride. Again, written according to the rules, and not worried about the balancing of the chemical equation right now. And so away we go. Aqueous lead 2 chloride combines with aqueous sodium chromate. That's all we got to say, cation, anion, to produce a solid lead 2 chromate and aqueous sodium chloride. That's what it says behind here, if you care. Down here. Oh, seen this one before on a previous slide. Sodium oxide. Here, carbon dioxide, water vapor, and so away we go. Solid sodium oxide, all we got to say, because sodium always has a +1 charge, combines with carbon dioxide and water vapor to produce solid sodium hydrogen carbonate. And that's really all we have to say. Already talked about this, that the coefficients indicate relative amounts in moles, right? And we could also interpret it in terms of molecules and atoms, but usually when we're balancing, we're interested in doing a lab experiment and trying to predict and then measure the outcome, and hence we're far more likely to be working in moles and then converting those moles into mass terms than we are to be working here, but again, relative amounts. Certainly the mass is conserved. If you were to take your mole amounts and convert them into mass amounts and add up the mass of the reactants, you would get the mass of the products. So it is certainly true that mass is conserved, but the coefficients themselves deal with moles rather than with mass. It works the same both ways. That is to say, we can interpret these relative amounts either going forward or going backward. Sometimes that will be useful to us. But then two things that we cannot tell from that balanced chemical equation are what the speed of the reaction is, and the speed can vary widely. And we also can't tell specifically what, if any, intermediate products might have formed in the conversion of the reactants to their final products. So it doesn't give us really a very good X-ray into the inner workings of the system, but it certainly does summarize the relative amounts and the events sort of from start, the view of what goes in and what comes out. And so most of the discussion of kinetics and intermediate products is not included in this chemistry class. It's typically the subject matter of more advanced chemistry classes, but we'll just go ahead and throw it out there so that you kind of have some sense of what we can tell from the chemical reaction as opposed to what we cannot tell.